I welcome our first speaker in this session. It's Sir John Pendry. John has worked in Cambridge, Bell Labs, Daresbury, and has been for a number of years in Imperial College, indeed more than 40 years. He studies many things: low energy electron diffraction, photoemission, negative refraction, invisibility, cloaks, many things, and he's made distinguished contributions in all those areas. His work has been recognized in a number of ways. The Isaac Newton Medal, that's the highest recognition that the Institute of Physics can bestow. Royal Society Bakerian Lecture, Royal Medal, knighted by the Queen, the Institute of Physics Dirac Prize, and a Kavli Prize in nanoscience. Today, he will tell us about extreme time modulation of material properties and Hawking radiation. John.
Inviting me to what this is proving to be a very exciting meeting. I worked in metamaterials for quite a while, and those, if you don't know already, are materials where the function is more down to the structure than to the chemical composition. And it's been an obvious extension of the metamaterial concept to structure materials in time as well as space. This has proved difficult experimentally, but now, in the past 2, 3, 4 years, experiments have come online which show that you can indeed modulate structures on a scale comparable with the period of the radiation that you're shining on them. And it's this encouragement that makes it a good time for theorists to start thinking seriously about these structures. So the first thing I'm going to do is to show you some experiments. These happen to be in the Blackett Laboratory in London, where I work, but there are other experiments around the world. Vlad Shaliv in Purdue, and also Moti Segev in Israel that do related experiments. We're going to, the first experiments are switching a material very, very quickly. And we had to ask the question, if we switch a material, how do we know how quickly we've made the switch? And the answer to that question we came up with was that we do a young slits experiment in time. So here's the experiment, and or the preprint with the experiment. I'll be careful not to fall off the stage here and cut the lecture short abruptly. So the experiment is a pump which blasts a layer of ito and kicks electrons into the conduction band. That pumping is aided by the fact that you have a gold layer here which has plasmons on it and nanoparticles and so on. I don't have time to go into that, but that's an important feature that enables the pump to give a strong enough kick to the ito that many electrons go into the conduction band, and so the ito changes from being an insulator to being a metal, and therefore reflective to a probe, which comes in at another angle. So when the pump comes in, it kicks a lot of electrons up, and then the electrons decay slowly. And instead of just making one of these pulses, you do it at another time with a given separation here. And by feeding these into a spectrometer, you can then make some deductions about how sharp that pulse is. So here you have a young slits experiment in space. Very familiar with this. It's been around for more than 200 years. The two slits diffract the light. The two slits in space diffract the light in K-space, which can be observed in the far field, and produce fringes. The spacing of the fringes, as you know, is the separation of the slits, but there's something else about the fringes, and that is the rate at which they drop off in space is the Fourier transform of the shape of each of the slits. And so looking at that decay, you can tell what shape these slits are. Now, the time equivalent of that is that you have two slits, if you like, which you're creating with this mirror in time, and this spreads the incident radiation out in frequency so that when you look at the different frequencies, you see fringes, which is a separation in time, and the decay rate tells you the shape of the slits, how sharp they are. And here are the data. This is a 800 femtosecond spacing for radiation of several hundred terahertz, and this is 500 femtoseconds, and you see these fringes are longer spaced, longer spacing in time, shorter spacing in frequency, the usual sort of relationship. And I should have mentioned before, actually, that these experiments were done in Riccardo Sapienza's lab by his research student, Romain Tirole, who was a student at the time, but is now a postdoc with us. Now, if you analyze those data, you find, very surprisingly, that the drop-off with frequency change is inversely proportional to the difference in frequencies squared. Now, that's very significant because the Fourier transform of a step squared goes as 1 upon omega squared. So this is telling you that as far out as we can measure, the upside of that step is too sharp to be measured. It's very, very sharp. How sharp? It's so sharp that the rise, is shorter than the period of the radiation. So we're getting very fast switching on the sort of timescales that we need to use to make theory interesting. So the experiments are coming along nicely. That's just a modulation in time, but what we really want to do is to make a modulation in space-time. And the simplest spatial modulation you can think of is a Bragg grating. And then we make it move in time. So you have this moving Bragg grating. Now, you don't want to do this by starting with a Bragg grating in material and shoving it along, taking the whole thing along. What you do is locally modulate the refractive index so that the profile moves whilst the material remains stationary. In that way, because nothing physically moves, you can have this Bragg grating move at any speed you'd like. Now, we can develop the theory for all sorts of Bragg gratings, but I take a specific one in which the impedance remains constant, but only the refractive index is modulated. And that means that any backscattering by the Bragg grating, any backscattering is cut off. So we're only talking about forward-traveling waves here. You may think, well, what's the point of a Bragg grating if it doesn't do any Bragg scattering? And that's the point of what I'm going to tell you about today. Of course, even though there's no Bragg scattering, no band gaps, and therefore, if a pure time modulation, there wouldn't be any parametric oscillations, but parametric gain, no band gaps, so no parametric processes. This device can, in fact, amplify and create radiation. And the key to seeing how that happens is this refractive index profile here. Now, I'm imagining that this grating is moving very, very quickly, and in the grating, because the refractive index varies, the light's going quickly here, and it's going slowly here, sorry. And at this point, I've made the grating go at such a speed that at this point, the light is going at the same speed as the grating. So if you inject light here, and in this part of the curve, it turns out that the change of refractive index is injecting energy into the system. So you inject energy here, and it doesn't stay there because the grating is going too fast for it, and the energy migrates to this point here. Conversely, if you put energy in here, it catches up with the grating, and it goes to this accumulation point here. And there's a singularity there where the light stops and accumulates and just grows forever. There's another funny point here, which I shan't pay much attention to. Okay. Now, there are lots of things you can prove about this particular grating. And when we're studying any physical system, what helps very much is if you have some conservation laws. Conservation of energy in mechanics is very, very important, but we're not conserving energy here because this system is time dependent. So you don't have energy conservation, but you do have quite a few other conservation laws. Here's the first one we stumbled across, and it is, if you think of a wave as a collection of field lines, then what you can prove is those field lines are conserved. And the way that the grating injects energy into the radiation is by compressing those field lines. Now, you know the experiment where you put a magnet near a superconductor, and the superconductor pushes the field lines of the magnet away, and you have to do work to do that. It's a very similar process to that. So you have this compression effect with the lines of force pushed together here, and this point here and here will be the accumulation point that I referred to in the previous slide. And you can see that what's happening to the radiation is that in each compartment of a period of the Bragg grating, you're getting these pulses, and these pulses, if you go through a finite section of the grating, these pulses come out sharp, more sharp if you have a thicker section of grating, and as you make it thicker, it goes on ad infinitum. And actually, that's the secret of doing the theory of these systems. You cannot have a sensible system which is infinite, because everything blows up. Infinite in space or infinite in time doesn't work. So you have to always think in terms of finite systems and come back to sanity at the other side, where there is no time dependence, and then just happened after going through the whirligig of this thing here, ask, well, what comes out of the washing machine at the other side? And that's what it is. So, oh, by the way, something that's also conserved is the phase. So the phase is dragged along in the same way as the lines of force are, and you get very rapid oscillations here. And of course, what that means is that you're making a very sharp pulse, and you're making a frequency comb here of very high frequency radiation. In fact, I'll show you that this is very hot radiation and has a thermal distribution. Now, the other thing that's conserved in this system is photons. So you say, well, a parametric oscillator, it puts energy into the system by giving more photons. It just pumps lots of photons in, and up the energy of the system goes. You can't do that here because the photons are conserved. Instead, what the photons do is they climb a frequency ladder. And so the energy of each photon increases in steps of h bar omega of the grating, and that's the mechanism by which energy enters the system, though there are exceptions to that, which I will come to in a moment. Okay, so I have a paper in Optics Express you might like to look at, which shows the proof of that. Now, apologies for this slide. I don't like to show lots of equations in my talks, but I think this implies an important point. So here we have Maxwell's equations, and what you normally do is to calculate the dispersion relationships. So in this case, we fix the frequency. Where's omega? Somewhere. There we are. We fix the frequency, and we're going to calculate k as an eigenfunction. And this is the matrix we get, and the matrix I've designed to be symmetric. So the eigenvalues are orthogonal, and that means they're independent. Okay. But the eigenvalues are not the fields themselves. They're the fields divided by the square root of this quantity, which is defined here. And that's the frequency of the particular level at which you're looking. So omega gains energy in steps of the frequency of the grating. And each amplitude of these various steps is weighted by this weight function here. And that's going to be very important in the conservation law. So the orthogonality relationship you get between modes is an orthogonality between these weighted modes. So you have a weight function here. And if you take, for example, the rate of change of the rate at which photons come out of the system, what you need to do is calculate the Poynting vector, which is just this quantity here we found in the orthogonality relationships, and divide it by the energy of each photon. So that's twice the energy, and that's the energy of the photon. Now, the significance of this is that what's conserved because of this orthogonality relationship is that energy is not conserved. We know that because the photon climbs ladders, but it's the photon number that is conserved. So if you have a mixture of modes, lots of different block modes together, you might say, well, I can add up the energy of each block mode, the energy flow. You can do that if the frequency is constant, but it isn't constant. So in a time-independent experiment, all the block modes contribute independently to the energy transport. So if you have a block wave which is going along with block symmetry, so it's the same amplitude everywhere, it conserves energy. And if you mix lots of block waves together, which have the same frequency, they conserve energy. I'm laboring the point because it's important, but if you mix lots of block waves together, even though they individually conserve energy, and you're in a system which is time-dependent, the mixture does not conserve energy. It conserves photons instead. So this quantity is not conserved, the flow of energy. You put energy in, and you can get anything out. Okay, so now I'm going to do some simulations of what happens if I put a plane wave. So I'm taking this impedance match system, so these waves are all going the forward direction, even though they scattered. They scattered in the forward direction, and then I'll start off with a plane wave, and what comes out of the other end is a mixture of plane waves of different frequencies and different wave vectors, but they're all traveling in the same direction. And then I'm going to count the number of photons. Okay, so here is what I've plotted here is essentially the mode number. That's the number of steps you've gone up the ladder. And the difference between these is the number of grating periods that the radiation has traversed. So the radiation comes in, out comes this pulse at the other end, and I count how many photons are in each mode. And you can see what's happening as the grating period doubles from 32 to 64, the population of these higher modes increases. So you're climbing the ladder. The energy is proportional to the mode number, and that goes like this. So that's what's happening, this ladder climbing process. Now, I told a little white lie at the beginning, and I said that this relationship, this flow of photons here, implies conservation of photon numbers. That is true, providing you only make transitions between positive frequencies. But the true photon number is given not by this, because you can't have negative photon energies. Even if a photon has a negative frequency, it has a positive energy. I think we can all agree on that. What is this? This is in fact actually the spin of the system. So you have a system which is a grating in this direction, but it's got rotational symmetry. It's a 1D system, so there's no means that you can add any angular momentum to the system. So this conservation law is simply an expression of the fact that the spin is conserved. Now that's the same as conserving the photon number, because all the photons are going in the same direction, if the frequency is positive. But if you make a transition to negative frequencies, then the spin of those photons created at negative frequencies is the opposite of the spin that you've put in. Okay, and that's what fouls up the system. So you have spin conservation, but that means that you don't always have photon conservation. And it's only this spin, or what I call the pseudo-photon number, which is rigorously conserved. So I told a little white lie, and in forgiveness, I will try and explain. I can't see this very well. Okay, so you'll start off with a given frequency here, and then you can move up in steps from a positive frequency to more positive frequencies. But the grating can also take you down as well as up. So you can go down in frequency, and you can go on doing that till eventually you make a transition from a positive frequency to a negative frequency. And that transition is not an ordinary transition, because it violates conservation of photons. And in fact, it violates it twice, because if you take a photon here and you change its spin so it counts negatively, there's one missing from the positive photons, and there's another one here at negative frequency. So what you've in fact done is created two photons. Two photons. So this process of making a transition between positive and negative frequencies is in fact a process in which you create qubits. And I'm going to talk about Hawking radiation in a moment, but if you read Hawking's paper, and believe me, it's quite an effort, what you will find deeply embedded in there is that he says that the essential part of Hawking radiation is that you make transitions between positive and negative frequencies. So negative frequencies are absolutely essential to understanding Hawking radiation, which is a process also of creating qubits, and very closely related to this process which I'm describing to you now. Okay, so this system will create qubits when it pushes you across plus minus frequency divide. So how many photons are created? So what have we got here? This is counting the number of photons at negative frequencies. And those can't get there by taking a positive frequency photon and putting it at a negative frequency. That can't happen. You can only get to negative frequencies by actually creating two photons. There've got to be two, because you've got conserved spin, right? Spin is conserved. So you create a positive frequency and negative frequency photon. And so that creation process can be identified by counting the number of negative frequency photons. And that's what I've done here. And as a function of the thickness of the grating, you see that this process of creation, so you index a certain number of photons, what fraction of them is turned into qubits? and this is the fraction here. So 20% in this particular case for these parameters here. If you're interested, I can tell you more details. And it saturates. Why does it saturate? Well, if you start off at a given positive frequency, which is fairly low in frequency, then you easily cross that barrier, because that's one of the first things you do. And then those photons there go skedaddling off to very, very negative frequencies. Likewise, those photons which have gone up go way, way up in frequencies, and the region near the origin of frequency is depopulated. And that's why the whole process saturates. Now, I did promise to tell you something about Hawking and his radiation. In case you don't know, and I'm sure you all do, Hawking predicted that a black hole, which is characterized by a Schwarzschild singularity in the metric, will emit radiation, black body radiation, and its temperature is inversely proportional to the mass of the black hole and the gravitational constant, and h bar, because it's an intrinsically quantum process. Thank you, Mike. I think I'm just about there. And the hassle about that, there's several interesting things about that. One is that it's the first phenomenon, the first quantum phenomenon associated with Einstein's general theory of relativity. Previous to Hawking, there were these two worlds of general relativity, which describe the ultimate massive universe in exquisite detail, and there's a quantum world, and the two never seem to talk to one another, and Hawking contradicted that and said that they did. I sometimes tell the story of how when I was a postgrad student doing a postgrad lecture course, Dirac gave the course on quantum mechanics, and at the back of the room in his wheelchair was Hawking learning the quantum mechanics that he used to do this. And he could just about speak at that time. It was a sort of gurgling noise that came out. And only Dirac could understand what he was saying. Brilliant brain, I suppose. He could decipher anything. And so we had to work out from Dirac's answer what Hawking's question was. Which also wasn't easy. Anyway, so what's that got to do with what I've been saying? Well, I promise you it has. So here's a Schwarzschild singularity. The metric is, Einstein thought about space as a bit of rubber. You know, it's just material like anything else, and it can be squashed by presence of massive objects. You can squeeze space, you can stretch it or whatever, and that squeezing and stretching is described by something called the metric. And it has a singularity in it when a radius, at the radius which is the Schwarzschild radius, which is proportional to the mass of the black hole. And the metric diverges at that point. Now, the other important fact is that as far as light is concerned, the metric is the refractive index. Okay, so the refractive index has a divergence in it, and it's that divergence which is producing the Hawking radiation. Now, unfortunately for Hawking, because you have to have an experiment to your theory to win a Nobel Prize, nobody's going to see Hawking radiation because this jolly big mass here makes this temperature extremely low, and so the radiation is very, very weak, and it's extremely unlikely that you'll see it unless we got some of these micro black holes that the people with tendency to worry thought that CERN might create at one stage, but didn't. Anyway, that's another story. So remember, the refractive index has a singularity in it like that. Now, you can do a transformation, a Galilean transformation, because this is not a truly moving object, it's a pseudo-moving object. You do a transformation to the rest frame of the grating. And if you then ask, well, what do Maxwell's equations look like in that rest frame? they look like Maxwell's equations, but with an altered epsilon and mu. Epsilon and mu are altered in the same ratio, and we won't talk about this much, but that's the coupling between electric and magnetic fields. But the important point is they have this singularity here, just like the, excuse me, and so does the refractive index, just like the metric does, and therefore this stuff should radiate. So we set ourselves on a mission to calculate what the Hawking radiation was from this moving grating. Did it do anything at all? Anyway, more hieroglyphics, sorry about that. But if you specialize to the case where epsilon is equal to mu, hang on, should be a minus sign anyway. What you come down with is this is the Hamiltonian, okay, and this line here is the ladder climbing process. So what you do is you annihilate a photon, and you create one in another energy state. So that's a ladder climbing exercise, and it conserves photons because for every annihilation operator, there's a creation operator, and vice versa. But then there's this second term here, which happens when you're making this transition between states of positive and negative frequencies. And there, this thing flips its sign, and you get annihilation, and creation in pairs, just as Maxwell said. An enormous amount of quantum mechanics in Maxwell's equations. It's just hidden because the photon is massless. If you write the Klein-Gordon equation, which is an equation for a massive boson, if you like, the simplest one, you'll find that h bar cancels when m goes to 0. And that's why Maxwell's equation is essentially quantum, but you don't see it because h bar cancels. Right, where was I? Okay, so this creates pairs. So the quantum mechanics seems to support this conclusion from Maxwell's equations that you can create pairs. So what we have, and there's a minor industry in laboratory black holes. So people have made all sorts of suggestions, UNRU particularly, for simulating black holes in the laboratory by making systems in which you have a singularity. And this is our contribution, if you like, to artificial black holes. But it is more than that because it makes a white hole as well. I won't dwell on that, but white holes are holes where things sort of do the opposite to black holes. Okay, so that's the singularity, which we're going to use to make Hawking radiation. Now, okay, so there is a problem because at the moment, although we can vary things in frequency at the same period as the grating, same period as the radiation, you can't, at the moment, I'm sure it will happen in the near future, but at the moment you can't actually make the grating move, all right? You can make it throb, but you can't make it move. Unless you move to quite low frequencies, and there the engineering becomes much simpler. Because the time scales and so on and so forth, you can see why. But the problem about moving to low frequencies is that photon energy gets very, very small, so you can't talk about counting photons anymore. So what do you do? Well, here's an idea. We know from Einstein that atoms which emit spontaneously. Okay, so you've got an atom and it's in excited state, and eventually that electron will drop down and emit a photon. But something else can happen. If a photon comes along, in a laser beam, for example, it can give that atom a kick and stimulate radiation. Two processes, and they have to coexist because of thermodynamics, as Einstein pointed out. Excuse me. Now, this system is no different in the sense that there can be spontaneous radiation of Hawking radiation, but also there can be stimulated emission, and the stimulated emission can be as big as you want, okay? It could be a phonon system because you're not counting photons or phonons. All you're doing is creating from a positive frequency a negative frequency. But how do you know that you've created a negative frequency? Well, there are two ways to do that. One is that if you're reversing the polarization of some component of the light, then that can only happen in this system by making a negative frequency. Because if the photon is traveling in the same direction, the only way you can give it an opposite spin is by changing the frequency. So if you see a spin flip, you've done it. That's stimulated Hawking radiation, SHR. You heard it here first. That stimulating process can also be seen in another way. Before I tell you the other way, let me tell you how much there might be. So what I've done here is the percentage of the incident power that gives rise to pair production, and this is independent of the frequency of the incident wave, by the way. Independent of the ratio of the frequency. So here are the parameters, but these are for two thicknesses of grating, 40 periods and 20 periods, and the percentage of the power created to Hawking radiation in each mode is given here. So you see it's quite substantial. And if you got a microwave source with 1 watt of power, looking at 10 milliwatts of power is not a big deal. So you can see Hawking radiation in the lab quite easily if it's stimulated Hawking radiation. Okay. So there's another way of finding out Hawking radiation, which is sort of mathematical. So if what you measure is the modulus of the frequency of the photon, so you start off with omega, and then you go up in steps of big omega, and then you calculate the modulus of this thing. And the modulus will always be that, modulo big omega. So if you knock off all the bits of big omega until you get to the smallest number before it goes negative, that's the modulo omega, okay? So that's what you get for positive frequencies. Sorry, right. Wait, one more slide. Here in front of me. Now, okay, so, but if you go to negative frequencies, then the modulus is different. And providing that the frequency is not a multiple of this, you get a different modulus of the frequency, modulo big omega, if it's a negative frequency or a positive frequency. So that's how you can tell conclusions. Okay, Mike's on my tail, so I'll please ask you to read those yourselves. Thank you very much.
Thank you very much. We're eating into time, but we must have some questions. A couple of questions, if the questions and the answers are short. Yes.
Thank you for the very enlightening talk. You described the creation of photon pairs by using this Bragg grating by virtue of the conservation of spin. Maybe it's a naive question, but what I want to really know is do these photon pairs obey the commutative relations in Fock states, for example?
I'm not sure. In what sense?
Because it seems to me that you have a very deterministic account of the number of states that you have generated.
Yes. Well, I mean, that is interesting because the original photon which goes through, which stimulates the radiation, is still there. So there are 3 photons, and they are highly correlated, if that's what you mean. And in particular, the photon you send through will herald the pairs. So that's quite useful. Okay.
Yes, Javier.
So I was wondering about the relation with relative friction, quantum friction, where also you have a pair photon creation as a mechanism, and in a way, it's also time-changing media.
Yes, that's right. I mean, I didn't have time to go into it, but if you look, you remember the sort of second or third slide I had where you had this compressed stuff. You can actually assign a Hawking temperature to that. And the interesting thing is that this is a purely causal reversible process. If you ran the whole thing backwards in time, reverse the direction of the grating, you could suck back this radiation and turn it into a plane wave again. But it's a temperature. And so it's one of the instances where you can identify a system full of information which already has a nascent temperature. It's in the temperature because they're all correlated. But then you can, if you forget the correlations, it becomes hot. So it's an insight into the quantum production of entropy, just as the quantum friction was. Friction is thought to produce heat. In the first instance, it doesn't. It produces a highly correlated system, which then sort of loses its marbles and becomes heat.
One comment before we move on. Among the fluid mechanical analogues that have been studied in the laboratory of horizons is a natural one, namely tidal bores.
Yes.
And the River Severn, near where I live in Bristol, is one of the rivers in the world where a wave moves and the front of the wave separates into the hole from out of the hole, upstream from downstream. It's actually a white hole, as it happens. But it's a natural phenomenon where this occurs. Thank you very much.
There's another bore near the Daresbury lab. It's on the D.
Yes,
not as big as your
there are
bores,
16 in the UK, actually, on rivers.
Okay, I didn't know that.
Yeah.
Thank you.
Good. Good, thank you.